ऊपर माई स्क्रीन है वहां पे क्लिक कीजिए.
Maybe lower the camera.
नहीं आप वो PDF का विंडो क्लिक कीजिए. When you do tomorrow?
I'm going tomorrow evening.
Yes.
And then 13th I plan to go. Pseudo break.
Okay, welcome everyone. You suggest we call this the Indigo Theory Seminar. So in spite of all odds, they not included multiple point cancellations. Indigo, I mean the thing that we use on stocks.
Yes.
The multiple flight cancellations later. Swarnalipa is here. Umang is also here, which we didn't expect. So Swarnalipa is a grad student at ISI Kolkata. She works with Saurabh Chakrabarty and Arijit Bush. So she's a math person by training, mostly works on questions in Boolean function analysis and related applications in CS. Yeah, I'm very happy to have her.
So already, Meenal already introduced me. So yeah, I mostly work on Fourier analysis of Boolean-valued functions on finite Abelian groups. And these are my collaborators. So this is the overview of the talk. So Z2, first I'll explain what is happening for Z2n, then I'll extend those things to finite Abelian groups. Then I'll state our results on pseudo inner product framework, granularity and pseudo dimension. Then improvements on Chang's lemma and Cohen's idempotent theorem. Finally, applications in property testing. So if I get time, I mean, if I have enough time, then I'll be extending random restriction and re-recording techniques for G. Okay. So, yes. Now, let f be a function from -1 + 1 to the power n to r, and where r is the set of real numbers. Now, any such function can be written as a linear combination of characters, where these characters are functions from -1 + 1 to the power n to -1 + 1. That is, any function can be written as summation f at chi, and these f at chi are called Fourier coefficients of f. And the set of all these f at chi is called the Fourier spectrum of f. And this hat above the set basically denotes the set of characters of -1 + 1 to the power n. And these two sets are in 1-1 correspondence with each other. So we take a function, a real valued function. That function can be written as a linear combination of certain monomials, which we call characters, and the corresponding coefficients are called Fourier coefficients. So these characters, they form a basis for the vector space of functions from -1 + 1 to the power n to r. And so the representation that we saw, that is unique. And studying these functions, I mean, one way of studying these functions is studying the Fourier spectrum of these functions, because the representation is unique. And now, consider those functions whose range is -1 + 1 or 0, 1 instead of r. These are called Boolean functions. And now the question is, does any set of f at chi yield a Boolean function? It turns out that no. So the Fourier analysis of Boolean functions is the study of the structural properties of Fourier spectrum of these functions.
Sorry, when you mean the set of values, do you just mean the, I mean, you know which character takes, or just as a,
It's a list.
as a list, not as a set? Okay. Okay.
Yes. So yeah, so these are, so Fourier analysis of Boolean functions is very well studied. These are two very common books that people usually follow. So first one is analysis of Boolean functions by Ryan O'Donnell, and this is higher order Fourier analysis and applications by Ahmed Hatami, Puya Hatami, and Shahar Lohet. So let us look at some examples. This is AND on 2 bits. It takes the value -1 if both the bits are equal to -1 and is 1 otherwise. And can be written like this. It is half plus half x1 plus half x2 minus half x1 x2. So here half, half, half and minus half. These are my Fourier coefficients, and 1, x1, x2, x1, x2. These are my characters. Second example is majority on 3 bits. This function takes the value -1 when -1 occurs more than 1 and 1 otherwise. And this function can also be written like this as a linear combination of these monomials. Now, one thing to note here is that there are other characters also which are present, but the Fourier coefficients are 0. So in this expression, 1, x1, x2, x2, x3, x1, x3, these are missing. So the Fourier coefficients are 0. So studies have been made on the Fourier spectrum of these
Do we have x1 square, x2 type of characters as well?
No.
We don't.
Yes.
So you're only plugging in +1 and -1.
Right.
When you square, it's always 1.
And a function, so if we take the range to be -1, +1, so Boolean valued functions, as we saw, can also be 0, 1 valued. But if we take the range to be -1, +1, it has some nice, interesting properties. One of them is Parseval's theorem. So by Parseval's theorem, it follows that the sum of square of the Fourier coefficients is equal to 1. Now, Parseval's theorem holds for any complex valued function. So this is what Parseval's theorem is. And range -1 +1 gives us the above property. Another important lemma is Chan's lemma. So it states that the characters corresponding to the large Fourier coefficients of a Boolean valued function are contained in a low dimensional subspace of Z2n. So I already stated that, sorry, yeah. Okay, yeah.
No,
Yeah.
sorry. I don't have a question.
Oh no, somebody, I thought you had a question. Yeah. Yeah. So I have already stated that Z2n and its characters, they are isomorphic to each other. Okay. So characters corresponding to, so this says that the characters corresponding to some large Fourier coefficients, they are contained in some low dimensional subspace of Z2n. And this gives an upper bound on the Fourier dimension also. So if we know the lower bound on the Fourier coefficients, so in that case, So if we take the threshold to be the lower bound on the Fourier coefficients, in that case, the large Fourier coefficients are all the non-zero Fourier coefficients.
Is this some kind of a decoding statement?
That is a bit of a
Which one?
no.
This statement, the fact that
No, it is actually an algebraic one, and
so you
So-
can think of an arbitrary Boolean function as a received word, and Fourier coefficients. So characters whose Fourier coefficients is large.
Yeah.
Are things that have large inner product. So this is like some agreement statement.
Yes, right, yes.
And this lemma seems to suggest that
The
all
all like structure on that list.
it's a
So it's like
the
Parseval will tell you that if the lower bound you want Fourier coefficients of at least epsilon, there can't be more than 1 over epsilon squared of that.
right.
But this is saying more like those also are going to lie in some
So this is the kind of statement we prove in
something
some
along that.
yeah.
Yeah.
Okay.
So I presume at some point will you have a quantitative version of this like
Yeah, so I didn't put it in this talk because it might have been, so this is a high level talk. So that's why I did not give in much details.
so but I presume the
Yes.
dimension of the subspace is a function of what your threshold thing is.
Yes.
So it's just a function of epsilon or also
No, so yes, so it contains epsilon. It contains, so in case of 2, no, there is no p, but yeah, right, yeah. So there are. Yeah.
Yes. I think so, that's how I remember. It's also a constraint.
Okay.
It's not purely, you don't have an ambient dimension.
but some polylog type.
Yeah, it could be like 1 by 1 is. Only log is, so right? Yeah.
No, I'm a little confused, but if we asked how many Fourier coefficients can be above, let's say epsilon,
Then you get.
Parseval tells you that it anyway can't be more than 1 over epsilon.
No,
squared.
But it
yes.
might.
But they are contained.
Expand the large
Not
dimension.
every one of them is. Not everything in that subspace is necessarily a large.
Yeah.
The dimension
Yes.
part.
No, but the
But I guess span is also then constant.
yeah, span is then constant, right? That's what I don't understand. I mean, then maybe I'm getting confused.
So maybe it's just a
Oh, yeah,
function of
yeah,
epsilon and it has to be something that's less than 1 over epsilon squared or whatever Parseval.
Yes,
Yeah.
yes.
Oh,
I mean, you're saying log of the, no, all of them could be linearly independent, but it will still be a purely a function of epsilon, the threshold.
Yeah. So,
Yeah.
okay, anyway, maybe.
Anyway, yeah,
Okay.
Wait, maybe I just remind me, is this the fact about the Booleanness or is it the fact from just that the function is bounded?
No, the Boolean valued, I mean, this is a fact for Boolean valued functions and that is needed in the.
I see, the bounded does not work.
No,
The bounded will give you something, right? And because of Parseval,
but-
it will give you something, but
maybe it would, but I'm not so sure whether it would. But Boolean valued, I mean, Booleanness is important over here.
Wait, I'm little confused. So
Hmm.
when you said that Boolean is important, you mean that like Parseval is giving us 1 because it's a.
Yes, so that is an upper bound.
Yeah, so what happens if it's like not 1 but constant?
Yeah, so if we don't have a Boolean function, no, but if we don't have a Boolean function, then the coefficients could be very small, like close to
Yeah.
0 or something. We don't want that. So, I mean, if that happens, then it would be, I mean, very dependent on the, what to say, order of the group.
What they order?
So here it is 2 to the power n, so that is.
Then that brings us back to the question, right? So epsilon is sort of dependent on n. So the threshold.
No, threshold we can choose. Let's choose threshold
Yeah,
to be
threshold
epsilon,
to be-
0.01.
Yeah, that's
And ask what the dimension. So that still makes sense. Okay, so
But anyway, let's
that's all.
Yes. And there's another important theorem called Cohen's idempotent theorem. So it states that any Boolean function with constant spectral norm can be written as a sum of small number of plus minus indicator functions of affine subspaces. And by spectral norm, I mean the sum of all f at chi r, absolute value of f at chi r.
Oh, just one.
Yes. Actually, Cohen's idempotent theorem holds for integer valued functions.
Why?
That is, so Cohen originally proved it, and later Sanders gave a quantitative version also. It apparently holds for. So I haven't checked why exactly. I mean, my approach is a bit different from what Sanders did.
The sum, you're not even saying it's a linear combination, just a sum.
Minus.
Plus minus indicator functions on some affine subspaces.
So an affine subspace will have spectral norm 1.
Yes.
And she's saying now basically,
And I think Raghu's question was just, is it like a linear combination of indicator functions of affine subspaces, or is it
No, no,
like
Maybe one of these additive
she wants it explicitly in this form of plus minus.
Okay. Okay. Okay.
Which is actually surprising.
Yeah.
You don't need large coefficient.
Uh-huh.
By the way, so
Yes.
the number, when you say small number,
Hmm.
from what I remember, this is, so I haven't worked, so, yeah, Cohen's I didn't know, but this Sanders guy, this guy is your theorem, isn't it like the dependence, the quantitative dependence on the spectral norm on the number of things that you
Yes,
is
yes,
doubly,
yes.
like even more than doubly
Yeah,
exponential,
yeah.
right?
It was
Very bad dependence.
Yes, yes.
W exponential in what? Oh, on the spectrum.
On the spectrum, that's what I remember. So I don't know about this Cohen's item, but I'm just talking about the original Sanders.
Yes, yes, yes. It was.
That's what
So
I.
in certain regimes, there were some improvements.
So this Cohen idempotent theorem is an improvement of Sanders or what?
No. So Sanders gives some
Oh,
quantitative
originally
version.
stated, okay.
Yes, originally stated by Cohen.
Okay.
Yeah.
Is it called the idempotent theorem? It seems like there's some algebraic connection here, right?
Yeah, I think so. Yeah.
So what is it?
It was proved twice and it was the same thing. I don't know.
Okay.
Maybe predictions are idempotent when you're talking about a fine space. It's clutchy.
I don't follow. So if it's just plus minus, how do you even do the majority on qubits? Does that mean as constant spectral now? And
No.
then you need the
I presume there'll be some dependence on n that shows up.
Yeah, ignore the end. I have variables, I ignore all of them. I just want the majority of.
No, so you can repeat also the affine spaces.
Yes.
Yes, I know exactly what the formula is. She showed it. It's x1 plus x2 plus x3 minus x1 x2 x3.
Yeah.
Divided by 2.
Yeah.
So how do you get the divide by 2?
Oh, how do you get the
So
divide?
it might be the case that, there's probably some affine subspace where it will look like there'll be some halves, etc. If you write the indicator function of that affine subspace in the Fourier basis, maybe you will get some fractions in the Fourier coefficient.
Yes, right. Yeah. So we consider all possible affine subspaces, and then.
So for the it's on equal to n equal.
Yeah. No. So like we saw in case of majority, there were 8 characters, but only 4 of them, 4 of the Fourier coefficients were non-zero. So number of non-zero Fourier coefficients is called the sparsity of f, and it is denoted by SF. And these Fourier coefficients of a Boolean function are integer multiples of 1 by sparsity. So this was proved by Gopal and al. Therefore, we have a lower bound on these Fourier coefficients now. So that is 1 by sparsity. So going back to Chang's lemma, so if we take the lower bound to be threshold to be 1 by sparsity, then one can get an upper bound on the Fourier dimension from there, from Chang's lemma. Yeah, so
We are going to set the threshold to be 1 over n.
1 over sparsity and yes.
So usually in Chang's lemma, is it like, do you define this large Fourier coefficients by considering it as multiples of 1 over s, or is that what you're trying to say?
No. By large I mean, so I consider some threshold. Let's say I'm given some threshold. So all the Fourier coefficients whose absolute value is above that threshold, that is considered to be large. And the range plus minus 1 is essential here. So for 0, 1 valued Boolean functions, this may not hold. So there are counterexamples.
Do you have something, let's say?
Yeah, I have. So you can take it to the top here. So there is a function, 0, 1 valued function, which is specified.
I don't want to counter them.
Oh,
So maybe do you have something that says that it's a multiple of 2 times s or something?
that was no. So there is a function which has sparsity 5, and the Fourier coefficients are 1 by 4 or plus minus half, something like that.
For 0, 1 value.
For 0, 1 valued, yes.
But
Yes.
Sorry, but we can always take the function and look at it as twice f minus 1 or something. So isn't a 0?
Sorry, maybe I don't understand the question.
So in the sense that suppose we just take whatever suppose the function was given to us as a 0, 1 value function.
Hmm.
Suppose I did something, what should I do? I do twice 2f minus 1. I consider the function twice f minus 1.
No, 1 minus, let's say.
Uh,
Because 0 corresponds to 1.
Doesn't matter. I mean, like I just want to map this 0, 1 to 1 minus 1. So taking twice f minus 1 will do this transformation for me on the
Yeah,
output
right.
side. But the Fourier coefficient at best, only the extra one thing might.
Yeah, right. That is possible. So the constant term may actually go away, or
Yeah, but the other coefficients are still going to be multiples of.
still remains a multiple of
no,
values.
sparsity will increase or decrease. Yes, or
Sparsity has changed by 1.
Yeah.
Sparsity can change by 1, which is a big problem.
No, but also the integer, I mean, isn't she saying that all of the coefficients are integer multiples here?
Yes,
So
yes.
when you do the minus 1, as you said, the minus 1 might ruin the whole thing, right? The principal Fourier coefficient might shift a lot.
No, it's by integer. If
If it is not.
Yeah.
Partially
Okay, but I agree that for example, suppose we said that if
Okay.
so suppose we said that if the function
Sparsity can change by 1.
Yeah.
That is the problem.
if the 0, 1 if it is 0, 1 value, suppose the statement was they're all integer multiples of 1 over sf plus 1.
No, maybe it was already.
Yeah, minus
Yeah,
1.
yes, because sometimes it might change.
Yes.
Sometimes it might change, sometimes it not change.
Okay, I take back what I said.
It's a multiple of 1 over sf.
I thought we can say that it's like 1 over sf plus 1 or something.
No, it's either that or it's one of them.
Yeah, but there are some Fourier coefficients that used to be whatever they were.
Right.
And now I have messed up one other thing. So, okay, I don't know. Okay. Okay, yeah, the sparsity has changed and I can't make a statement on this. Okay.
Now, so this is another theorem by Zhang et al. It states that for any Boolean function with constant spectral norm, there exists an affine subspace of small codimension such that the restriction of f on that affine subspace is constant. Okay. Yes. And yeah. So there are other structural results concerning the Fourier spectrum and certain conjectures also. And so this Fourier analysis of Boolean functions has lots of applications in cryptography, coding theory, circuit complexity, pseudo-randomness, learning theory. Here are a few. And okay, so till now we saw functions on z2n or minus 1 plus 1 to the power n. So one can also obtain a Boolean valued function on changing the domain. So instead of z2n, I take some other domain d. Now, when D is a finite abelian group, F has a lot of applications in theoretical computer science. So, like we saw in case of Z2n, here also any F can be written as a linear combination of certain functions which we call characters, and these characters are functions on G, and they take values in roots of unity. And these coefficients f at chi, they are called Fourier coefficients.
So first of all, this talk, what should I think of D as, like FP or something? Or,
Yeah, so it is a finite abelian group, just a finite abelian group. ZPN is also a finite abelian group, but by finite abelian group, I mean, so it has, what to say, maybe I'm just right.
I think
Yeah.
No, I think I understand what the abelian group is, but it's like, is there a particular example that is helpful to keep in our heads when we are thinking of G?
That is, no, I haven't actually. So I have given two examples, but just for making people familiar with the, so not
the
really.
theorems you're going to state later
Yeah.
will be for general.
Abelian groups only, yes. And Z2n is a finite abelian group, and G equals to Z2n is actually a special case. Also, like in case of Z2n, G and G hat, these two are isomorphic as groups. G hat is the set of all characters that also forms a group. So this is one example of a Boolean-valued function on finite abelian groups. So here the finite abelian group is Z3n, and it is defined in this way, that is if x takes the value -1 if all the coordinates are equal to 2, and it is 1 otherwise. And this is another example. So here we take G to be equal to Z4 to the power 2n, and so f of xy takes the value 1 if x dot y is even, and -1 if it is odd. So here x and y comes from Z4n. So we saw certain results for Z2n. Now the question is, can those results be extended for Boolean-valued functions on G? Some of them can be extended. So first one is Parseval's theorem. So we saw that Parseval's theorem, so in case of Z2n, Parseval's theorem, so it follows from Parseval's theorem that summation f at chi square is equal to 1. Here we have some mod over here. So we are taking absolute value square. So this is because the Fourier coefficients are now complex numbers. So again, Parseval's theorem holds for any complex valued function, and range ±1 gives us that property. So this is a version of Cohen's idempotent theorem for G. So it again states the same thing. So any Boolean valued function on G with constant spectral norm can be written as small number of sum of plus minus indicator functions of cosets. So in that case, we had affine subspaces. Here we have cosets. And Chang's lemma also states that the characters corresponding to the large Fourier coefficients are contained in a low dimensional subspace. And it gives an upper bound on the pseudo dimension of Boolean valued functions of G. So what is this pseudo dimension? So that I haven't yet defined. I'll define it later.
What is the low dimensional option? Okay, so this is the
Yeah. So again, here also G and G had, so yeah. So
I mean, for example, if G was something like Z2 to the n, where I can think of it like, okay, each coordinate is like Z2, but I have n dimensions in some sense.
Yes, right.
There it makes sense, but
Yeah.
it's like
Here there is no concept of, so that's why pseudo dimension comes.
No, but
Because
suppose
we don't-
Is like a large cyclic.
Yeah, right.
what should I
But
think of as dimension then?
yeah, so by dimension, so
Oh,
in that
prime
case,
order.
we don't have a vector space structure. So there is no concept of dimension over here. So instead, we define some pseudo dimension and use it to, yeah.
You are extending it to closest vector space, something like that.
Yeah, not exactly a vector space, but yeah, something so that I could explore the cosets and all. Yes.
No, so I was saying you're going to define later
Yes.
something which is the analog of a linear space
Yeah.
for groups.
Yes.
Okay. When you say low dimension, you mean low pseudo dimension?
Low pseudo dimensional. Yes.
So you define what is the pseudo dimension in this relation.
Yeah. Yeah. Yes. I will.
No, I'm really confused now. So the point is, so I guess sorry, what if G doesn't have any subgroup?
Nah, G, so any abelian group, any finite abelian group will always have some
Prime order
subgroup.
thing,
Yes.
yeah. If it's a prime order thing, what happens then?
Yeah, so in that case, things will, we will work with only one subgroup, or everything will follow up with that subgroup only, yes.
No, but then chance lemma would not give me anything, right?
Yeah, that is a very bad, yeah, but.
Should we think of G as like a
Fixed
Cartesian?
group,
like there's a core group like Z2 and then the n-dimensional. Should we think of
That's a bit,
that's not necessarily not be a vector space?
Yes, so.
Is that a good concept?
Yeah, no, actually, yeah, so any abelian group, finite abelian group, I'll come to that. So any finite abelian group can be written as cyclic.
No, that is true.
Yeah.
The point is like if I take a large prime
Yeah.
and look at ZP.
Yeah, then that is a bad
then-
case. That is actually a bad
you
case.
may anything.
No, that is a bad case, yeah.
So is it fair
So how
to
is-
sort of say that, Chance lemma will give us or rather the generalization of Chance lemma to more general groups will give us a meaningful statement if G has
Some, let's say, constant exponent. So by exponent, I mean the order of the maximum order an element of G can take.
okay.
So we consider that to be constant.
I see. Okay.
Yeah. So again, I skipped the formal statement because I thought too many expressions might actually confuse people. That's
So
why.
the maximum order of any element in G is small. But this is a bit like what Mrinal was saying, right?
No, yeah, right. So Z2n, in case of Z2n, it is 2. So that is a good case. Z2 to the power n.
No, same like for example.
Yes,
same thing.
but if we take a cyclic.
Looking at it and breaking down
Yes.
the direct product and.
Yes, right.
Slightly different, the elements that still have different orders.
Yeah.
Yes.
yeah, if there's like, for example, ZP and ZQ idea, then there's an element
Yes.
called PQ. No, sorry. It's not okay.
But yeah, if we take a cyclic group, then that is a bad case. Yes.
Just having small concepts.
Yeah.
So this.
So the other thing is like, is it motivated from what you're doing? Is it motivated abelian group from some applications in mind where certain kind of abelian groups frequently occur?
Yeah, so these abelian groups with bounded coefficients bounded exponents have applications in additive combinatorics. In some cases in theoretical computer science also. So Cohen's idempotent theorem have multiple applications in additive combinatorics, and Chang's lemma has applications in learning theory and also in additive combinatorics. So So there are certain things that can be extended, as I already stated. So improvement on Cohen's idempotent theorem has already been done for zp to the power n, where p is a prime. So note that we already have the vector space structure over here. So that was done by Spilka et al. And improvement on Chang's lemma has been done for Z2n by Chakravarti et al. Granularity for Fourier coefficients is known for Z2n, which was proved by Gopalan et al. And upper bound on Fourier dimension for Z2n was given by Sanyal.
What is grand?
Yeah, granularity. By granularity, I mean that. I stated that Gopalan et al. Showed that the Fourier coefficients of any function from Z2n to plus minus 1, they are integer multiples of 1 by sparsity, right? So that result is called granularity. Yes. And yeah, and upper bound on Fourier dimension was given by Sanyal, Chakravarti et al. You know? So my research area is exploring structural properties of Fourier spectrum of Boolean-valued functions on G, and finding algorithmic applications of these structural results. So now, what are the challenges that we face with finite Abelian groups? The first challenge is that the Fourier coefficients and the characters, they are not real numbers. So because of that, the Fourier coefficients of Fourier coefficients of f are complex valued whenever G is not equal to Z2n. And most results use this fact, so they cannot be generalized. For example, no ordering. That is, there is no ordering in case of complex numbers, and that is an issue. So I haven't given the example over here. So there is so I already stated that Zhang et al. Showed something that if we take a function, Boolean function, and with some constant spectral norm, then there exists some affine subspace of low dimension, which if we restrict f on that affine subspace, it becomes constant. So their proof technique heavily uses this real valued nature of the Fourier coefficients, and apparently that cannot be generalized. And the second challenge is no vector space structure. So results on Z2n also use the fact that Z2n is a vector space, and those cannot be generalized because G is not a vector space. But some results can be generalized when G is equal to ZPn, where P is a prime number, because the vector space structure is still there. And for example, Spilka et al. Showed the following result. So the statement I have given here is looks same as Zhang et al. But Zhang et al.'s bound given for Z2n is much better compared to that of Spilka et al. So Zhang et al.'s bound was linear in spectral norm, so it was order of a spectral norm, F1, and Spilka et al.'s bound is square of that.
The Zhang et al. Directly follows from Zhang lemma, or am I missing something?
No.
It is getting.
Yes, it has a separate proof, and their result is actually a better one compared to that of Spilka. For Z2n.
What am I reading wrong? Sorry, go.
Yes.
Oh, no, you can ask that.
No, I'm just trying to, see, so this theme U that you wrote.
Yeah.
I'm trying to see what happens if I choose G to be Z2 to the familiar Boolean domain.
Yes.
And if I have like, the indicator of an affine space of large codimension, very large codimension, right? So it will have, every affine space has spectral norm 1, the indicator, right? Now,
so it is.
why will it be now a constant on a small codimension? Is this?
Yeah, so there will exist.
There will exist some other thing.
Yes. So there exists an affine
The
subspace.
function is already an affine indicator.
No, but that affine space has very large codimension. suppose I take an affine space of very large codimension.
So that's the same thing as saying that's very small dimension.
Yeah.
Which basically means that I can, if I choose an orthogonal part of it, then I'm always 0.
Oh, right.
Yeah. Yeah.
Oh, so it's f of v, it's not, I'm sorry, yeah. I was just looking at the Fourier spectrum would be constant or something like that.
So, like, I don't know, Chandra, you said that like these large Fourier coefficients,
Yeah.
they're constrained in a small subspace, like low dimension subspace, right? So when you're talking about the Zhang et al. Result, which is the Z2 version of this.
Chang's lemma also had a lot of other things.
Maybe,
Yeah,
maybe,
yes.
So the Zhang et al. Result, when you're saying that, okay, if you're constraining to that subspace,
Yes.
if you set an appropriate threshold, won't it become constant?
Yeah, no,
Like,
but
I mean, if you set the threshold to be all like non-zero.
yeah, but Zhang et al. Gives a bound on that. So it gives a bound.
It could come from Chang's lemma directly.
No. So Chang's lemma, from Chang's lemma, we have an upper bound on the Fourier dimension. But here we don't have an upper bound on the Fourier dimension. All it is saying is, yeah, so there exists some affine subspace. If you restrict on it, yeah, it becomes a constant.
Okay, so this dimension comes from Zhang.
Yes. Dimensions already exists over here because we have
No,
vector
the
space.
Zhang et al., the Z2n version of this.
Yes,
so
Z2n.
Zhang et al.
Yes.
Gave this the construction of basically.
Yes.
Yes. It's trivial. Right? G is trivial.
And why is that true? I mean, the G
Oh,
at
for
two
constant
positions.
spectrum, sorry, yeah.
Huh.
For one it's trivial.
Oh, not for one. Okay. No. Okay. Oh.
Then I'll just go to our results part. Oh, I don't have much time, but okay, I'll try to. Achha. So this is my so I'm just stating this because the expression for pseudo dimension contains a t and all and whatever we have over here. So any finite abelian group can be written as a direct product of some cyclic groups. And here pi are primes, but they are not necessarily distinct. Okay. So by exponent, I mean the maximum order an element of the group can take. And pseudo inner product operator is defined by something like this. So this is a framework that we use to bypass the vector space structure.
So you're going to define duals, etc., using this method?
Yeah, sort of. Yeah. So here in this talk, I won't be getting into the details, but yeah, we'll be using this framework. And yeah, so at first, so again,
Why did you think of that pseudonym? Like,
yeah, so that actually involves, so if you look at the characters, so one can think of the characters as roots of unity. Now if you take the, so if you look at the characters, something like this come up above the roots of unity. So that is sort of a motivation. So constructing character decision trees and all, this thing helps once you have that. Now, in case of G, this is how one defines granularity. So complex number is K granular with respect to G. If that complex number can be written as G omega delta by delta to the power K. So here G omega delta is some polynomial in ZX. And by omega delta, so omega delta is the delta x root of unity, primitive root of unity.
So there's no constraint in what the G might be.
Sorry?
Oh, it's
This
an
G,
integer polynomial.
yes,
Oh, it's an integer polynomial.
some integer polynomial,
Okay.
yes.
can you say what the method is?
Sorry,
What is omega delta?
Delta.
sorry. Omega delta is the delta is primitive root of unity.
Oh, sorry, delta was this.
Yeah, that exponent of the group. Yes, delta was the exponent of the group. And implementing the pseudo inner product framework, we get this. So in case of Z2n, the lower bound was 1 by sparsity because the Fourier coefficients are integer multiples of 1 by sparsity. In this case, the lower bound is given by something like this. It is 1 by 2 into sparsity whole to the power phi delta by 2.
What is phi?
Phi is Euler's totient function, so that is basically number of yes, co-primes, yeah.
So when you say like x granular, you mean like integer multiples of 1 by x?
Yes.
Sorry, I was also thinking, oh, maybe I should think of the granularity statement as a contrapositive of this in some sense. Because normally we would want to say, make a statement like, if someone had promised to me that the Fourier, the Fourier norm is small, then I will be able to make a statement of the form that, the Fourier coefficients can't be completely crazy. I mean, the denominators are.
Yes, right.
bounded.
Yes.
So this,
Yeah, here we have some nice structure on the Fourier coefficients. That is, one can show that Fourier coefficients are something granular. That something is dependent on sparsity, not on the order of the group.
so because the part that is sort of bothering me is just the following. So in the sense that, because this looks like a lower bound on the Fourier norm.
Yes.
Sorry, someone.
No, I say that every, so, I mean, you can, yeah, so lower bound of, when you say that the lowest the Fourier coefficient in magnitude cannot be any lower than that. But it is also, whatever, k granular or k is.
Oh, sorry, that's not the Fourier norm. Okay, so it's like, this
That
is
is
like
the
saying that
magnitude.
every Fourier coefficient, it has to be at least this much.
Right.
Oh, I see.
And
Okay.
moreover, they are
Sorry.
also k granular for where k is.
Okay. Yeah.
That's what.
Yeah, right. Yes. So from K granular, in case of Z2n, we had that lower bound 1 by sparsity, but in this case, we cannot say anything like that. So
This is every coefficient, they can't even be 0.
yeah. So non-zero coefficients.
Non-zero.
Sorry, I think I forgot to mention. Sorry. Yeah. So the non-zero Fourier coefficients are they satisfy this. And preliminary version of this.
How good
was-
is
Sorry?
the right answer for this? The bound?
Oh, the bound. Yeah. So the thing is, we haven't yet shown. So I was coming to that. So we haven't yet shown that the bound is tight, but there exists a function which has a Fourier coefficient strictly less than 1 by sparsity. So the linearity, so the linear bound that we had in case of Z2n, that we cannot have over here. Yes.
Sorry, repeat again.
Yeah. So we had that linear thing, linearity.
One over SF.
1 over SF, but in case of Z2n, but in case of any group not equals to Z2n, so we have constructed a function on a G which has a Fourier coefficient that and it has absolute value less than 1 by sparsity, strictly less than 1 by sparsity.
So you don't know whether this is tight, but you cannot hope for anything as good as one over S. That's
Yes.
Okay. And the group is a crazy group or what?
No, it actually what to say. So group could be ZPN also.
Okay.
So it fails
No, the function-
Z5. The function is a bit of.
Sorry, I mean the counterexample is for some group like Z5 to be.
Z5 to the power n or Zp to the power n or even for G. For Z3, surprisingly, things are really not that bad, but yeah.
For Z3, everything they call functions are fine.
Yeah, so the thing is for Z3, there are certain things that hold. Okay, so what happens is we don't have integer multiples of 1 by sparsity, but this G omega delta is, so absolute value of that thing is greater than equal to 1. This one could say. These things come, but they fail when we have Z5 to the power n or higher groups. Yes. And sure. So yeah, I just wrote it just to be. So this is a sparsity testing result that we also did. And I haven't included it here, but I'll state the result later, just an application as an application of these results. So this is the function that, so this is AND of some thresholds.
So, and what are those? So that's an indicate.
Yes, threshold. So these are, yeah, right, yes. One, indicator functions only, and these. And this function has a Fourier coefficient. So this function has sparsity p to the power n. So here I have defined it for z p to the power n. One can extend this function for g also. So sparsity is full, that is p to the power n, but there exists a Fourier coefficient which has absolute value 1 by p to the power nc, where c is c is strictly greater than 1. And for p equals to 5, we have c to be something like this. And this is an open problem. Constructing a function that actually achieves that bound.
So for starters, constructing a function where this lower bound depends on delta.
Yeah, right. Yes.
Is there some intuition that delta must show up, or is it something that came out in the proof?
Yeah, it actually came out in the proof. So since those polynomials are involved, g delta and all that, so we had to bound it somehow. And to do that, using some algebraic number theory results gave us that bound. So delta was coming. Now I'll define the pseudo dimension that is stated. So yeah, so f be a Boolean valued function and support of f at is the set of all characters with f at chi not equal to 0. And since, so I already stated that no vector space structure, hence there is no concept of basis over here. So how can one define the dimension? So by pseudo dimension, we mean this, that is support of f at. So pseudo dimension is the size of the smallest gamma such that support of f at is a subset of the subgroup generated by gamma. So there are various notions of dimension when we have an abelian group. This is one of them, and we will be, so this is, yeah, so you're working with that.
Smallest generating set.
Yes.
It's pretty natural.
Yeah.
Hmm.
Yeah.
So now again, implementing that pseudo inner product framework, we obtained this result. So yeah. So sorry, I wrote that delta f, but in this theorem we don't need that delta f. So the pseudo dimension satisfies this. That is order of square root sparsity log sparsity. So in terms of delta, there is another bound, that is sparsity delta f log sparsity square.
So this is what, and this answers some of the questions we had about Planck's lemma here. This bound is better than SF.
Yeah.
Yes.
Sublinear in SF.
Yeah.
So Z2, the Z2 version of this was done by Sanyal.
Yeah. Yes, square root of sparsity, I remember.
Yes, square root sparsity, log sparsity. And Z2 version of the delta F thing was done by Chakravarti et al. It was some square root sparsity, delta F, log sparsity. So that was in fact an improvement of Sanyal's bound.
I'm sorry,
Yes.
missing something.
Hmm.
Where is delta F appearing?
No. It is not appearing. Sorry. So this is a typo. But there exists another result. So I mean, we have done it. So it involves delta F, and it also
So there are two versions, one which involves sparsity and the other which involves
delta F and sparsity.
sparsity.
Yes.
Yes.
So in case of Abelian group, we have a square of that thing, that is sparsity delta F log sparsity squared. And that is, these two are not comparable, cannot be compared. And yeah, so there exists a coset of codimension this such that F restricted to V is constant. So this is a generalization of Spielka et al.'s result. So this is the, yes.
Plus F at 1 square, so that's the
Yes.
spectral norm square.
Square, yes. So we could not generalize, Zhang et al. Cannot be generalized for finite abelian groups. So in fact, the square thing that is coming because we are using Spielka et al. We could not use Zhang et al. In case of actually Sanyal also used Zhang et al. We could not do that, but there is another result by Sanyal and Monday. We generalized that.
Yeah, for Nikhil
Monday, yes. So we generalized that and used it, and hence got this square root sparsity log sparsity bound. Yes. So I don't think I have, no, it's already 5. So I'll just take 5 more minutes to explain. Yeah. So Chance lemma and Cohen's idempotent theorem can be can be improved. So our results give an improvement of Chance lemma for functions with bounded exponent. For groups with bounded exponent. Finite abelian groups with bounded exponent.
You see,
Yes.
your result gives an improvement of chance level over
Z2.
even Z2.
Yeah, for Z2, Chakravarti et al. Showed that there is an improvement.
Nice.
Yeah, so we showed that the chance lemma can be improved for finite abelian groups and with bounded exponent. Also, another thing to note here is that the notion of dimension by chance lemma is different. So we denote it by d chan over here, but pseudo dimension and chance lemma, they can be so the chance lemma d chan is equal to theta rf, and hence the comparison can be done. But yeah, so we always assume the bounded exponent thing. Achha. So another open question is, can chance lemma be improved further? And similar thing for Cohen's idempotent theorem. This is the original theorem, and we have showed that it is so our result is an improvement for functions which satisfy something like this. Something like this. And again, the same open problem that whether Cohen's idempotent theorem can also be improved for.
More general case of groups, or like you're looking at.
Yeah, so we assume bounded exponent, constant exponent thing for the groups that is needed, and given that we also have this thing.
No, I mean like
Yes.
open problem. So
Yes.
I'm not understanding. So you're looking at things like tar groups and stuff like that.
No, not really. So we have done it for constant exponent thing.
Yeah.
So the first open problem will be, can one bypass that constant exponent part? So like Arkudev was saying that if we have some cyclic group Zn, let's say, so that is very bad. So that is a bad case for our yes. So can it be done for things like that or something? And applications in property testing. So this is some testing sparsity result. So there exists some algorithm, a query algorithm, which tests whether a given function is sparse or it is epsilon far from sparse. And this was published in MFCS. And this is another result. So we define some automorphism distance. I'm not really getting into the details because I don't have time. And using that, one can, so testing isomorphism of Boolean function is basically, so we are given one known function and one unknown function. Let's say our unknown function is f. So we determine whether the automorphism distance is less than equal to epsilon or greater than equal to something, some epsilon plus tau. And so there exists an algorithm which does this in making some order of m to the power 8 by tau to the power 8 many queries. Here, m is the spectral norm of the known function. So these two results are there in random 2025. And okay, so I'm skipping this. Just
For these results, the Z2 to the n versions were known, or the applications that we have.
yeah, so Z2 part is known again.
And so the new thing in the theorem is the fact that you have it for arbitrary finite Abelian.
Yes. So another thing to note, I wanted to say is that the bound that we had for dimension, zero dimension, that square root sparsity, log sparsity, that thing is independent of the exponent of the group. So we don't have to assume constant exponent for that. The other results that followed from it, they use, so for that we need, for Chang's lemma, Cohen's idempotent theorem, for that we need the bounded exponent part.
This third result, structure of sparse Boolean functions. What kind of structure do you give that granularity structure?
Yes. So granularity structure, lower bound, and using that we do that testing sparsity thing.
See,
So sparsity testing algorithm, is it similar to the Z2 case?
Yeah, it is. So the main issue was, so the main challenge was defining the granularity, because so there could have been multiple notions of granularity. We tried with mod f at chi, it did not work. Real part or imaginary part of f at chi did not work. Then so yeah, it took us some time to arrive at that. Yeah. And then getting the lower bound also another thing, so that also doesn't follow directly. So.
can one define, so I mean, there's a natural notion of degree also, right? You talk about sparsity.
Yeah.
If I look at what, let's say, Z3 here, now these are no longer multilinear polynomials.
No, something in roots of unity. Yes.
You can define them, so you can define the degree of a total function.
Yeah, that we can define.
Approximate degree.
Yeah, right.
This is known, like, for example, is Nisa.
No, we haven't tried that yet. So I was talking to Mrinal about it. So I thought of trying those things, but there is an issue. So what to say? So you need to find applications in theoretical computer science. Otherwise, it becomes
asking a pure.
Z2 has applications extend to those.
No, but without this application, like.
Yes.
Have people even defined this approximate degree?
No.
Nothing is known.
No.
Now the degree is a little bit of fuzzy concept, right? Because it's no more the.
Oh, you can just take the sum of the individual
Yes.
degrees, like the degree of a polynomial.
But like so there will be like so you'll treat omega and omega square, for example, differently but they're not so different. Right?
No, what he's saying is
Z3. So you treat the character has omega in a position versus omega square in a position. You treat them as different degree or same degree, or which one is higher degree?
And maybe rather than degree, maybe it's the support size.
Yeah, support size is probably
Yeah,
right.
how many
Yeah,
different
that will
points?
agree in the Boolean case to take support size.
I'm not sure whether that is the right way.
Yeah, but I don't know.
I don't understand.
But yeah, I think what Orkodev said, that is more natural one. If we generalize it, so considering all the Fourier coefficients, so sorry, not the Fourier coefficients, the characters. So if we sum up the powers.
No, but the powers, like example, omega and omega square are essentially isomorphic, right? If I define I differently, omega will
Yes.
by omega square, omega square to omega. There is
Oh, no.
inherently limit omega and omega square.
Acha, no, actually omega is that particular primitive root of unity, that is 2
No, but-
pi I by.
But there can be two primitive roots. It was that
We take just one particular
You
primitive.
take a primitive root
Yeah.
and then define
and
degree.
then define
Yes, yes. So
And maybe you explain all then it
yeah. So characters are actually defined like that only. So we take, we usually take omega to be 2 pi e to the power 2 pi I.
I mean, yeah,
by,
but you could define the other like
right, exactly. Right.
choose one and then now
Yes.
define.
No, but I
Yes,
guess
yes.
Piyush's objection is just that then the degree is not a property of the function.
No, I think maybe
It's going to be a property of the representation.
No, but it could be that it could be.
yeah, it could be that because of you
Because of moving around, it will be the same.
just transform in a way that
Very good, the invariant of this chart.
yeah, that's what
Oh, yes. Okay. Okay, one other question. I was just curious.
Actually, I think that it is impaired.
Yeah.
yeah, it should be.
Yes, it should be. Yeah.
Just it should be.
Yeah.
So,
Hypothesis is false.
the example that you had where it was like an and of thresholds on each coordinate. I was just wondering, if you wanted to sort of check if the delta should show up in the lower bound for the Fourier coefficient, the natural thing is to take the group to be ZP1 cross ZP2 cross ZP3, where you just take the first few primes. And define the AT function similarly.
Yeah, then also it won't.
The lower bound is not good enough.
No.
Oh,
Yes.
okay. Nice. Okay.
So sorry, we can talk after we talk.
Mhm.
I mean, so I have people, because there's parity decision tree, right?
Yes.
So these computational models are, so they're like this, you take like, you can ask this sort of linear function questions, queries.
Yes.
Over, so for instance, Z3 to the n, have people looked at that? Like, do you know?
No, I don't think so.
Interesting. Because, that should give rise to a certain notion of degree.
Yeah. No, I haven't found anything related to approximate degree for. I don't think there exists any related to approximate degree for finite Abelian
So
groups or
how
higher
did
groups.
you to look at this kind of questions?
So firstly, the Chang's lemma was the thing that we wanted to improve, and then many things came up and all. Yes. So there already existed an improvement for Z2n, Chakravarti et al. Did. So since Chang's lemma already exists for finite Abelian groups, we wanted to check whether the similar thing holds for finite Abelian groups also. But yeah.
Further questions?
Not just time.
Yeah.